Hello everybody. Let us start our discussion today. We will take up from where we left last time. We defined the Riemann curvature tensor, which is written in the first line over here in its full glory. It is written, if you look at, in terms of the derivatives of the reciprocal symbol or connection, affine connection, and the second order terms in affine connection. So the second order terms in affine connection will be the multiplication of the first derivative of g. On the other hand, the derivative of affine connection is second derivative of g. In the local inertial frame, it took this form where the affine connections are 0. So in local inertial frame, this is essentially related directly with the second derivative of g. Then we looked at identities and we proved some I left for you to prove, which you can use the local identity in the local inertial frame, the expression for r in the local inertial frame. And then we looked at the Bianchi identity where we take further derivatives of the Riemann curvature tensor. So today we will define a few more tensors which is related to the Riemann curvature tensor and are immensely important in general relativity. So let's define the Richie tensor. The Richie tensor is, if I call it R alpha beta, so it's a tensor of type 0, 2. If I write it in this form, this you get by contracting the Riemann curvature tensor with the first and the third index. Okay, so this also you can show that this is equals to beta alpha, which is that it's symmetric about its indices. Okay, now it turns out that obviously I have 3 indices downstairs and 1 index upstairs for the Riemann curvature tensor. I can contract it with any of the indices. Why do I contract with the third index? It turns out that if you contract with the first or the third, the first or the fourth, then it is 0. So I'll just show you once. So this is a small exercise, and I will do half of it, which is that I will show you that if I contract with the first index, then it is 0, and you have to do for the rest. So what do I do? So what I do is the following. So I have, to start with, I have this R lambda alpha mu beta. I multiply both sides with multiply this with g lambda eta, which gives me the Riemann tensor which we have looked at last time, all downstairs. Now, in the left hand side, I further multiply it by some, say, eta alpha, such that this is what I get in the left hand side. This equals to g eta alpha r lambda alpha mu beta, right? So let's see what we have in the here. So here, if I look at these two g's, it's essentially Dirac delta. What about here in the right hand side? You see that I'm sorry, I should have eta here. And this also should be eta. That's what I get. So lambda get contracted, so eta comes downstairs. So now here, see eta and alpha both are dummy indices, they're summed over. So why not you interchange them? So we write this as G alpha eta and R alpha eta, and then mu beta, I leave it as it is. This thing becomes, so this is that I have to change the index alpha by eta. I'm sorry, I have done a mistake here also. So this should be lambda. So I have to change the index alpha by the index lambda, because here eta is summed over. So this is a delta function alpha lambda. So I change the index lambda by alpha. So I get the contraction of Riemann with the first two indices in the left hand side. What about the right hand side? Well, if I look at the right hand side, the right hand side is G is symmetric, so this I can write as eta alpha, but R is anti-symmetric. Remember the identities, so I will pick up a minus sign if I want to write it in terms of this. And if you compare these with that, you realize that something is equals to the negative of something, which means that something is 0. So that tells us that if I contract the Riemann between the first and the second index, then it's 0. So that will not give you any useful tensor. I mean, it will give you a tensor. All of its components will be 0. So we define the only non-zero way we can contract, which is the first and third index of the Riemann, which gives it the Richie tensor. Okay, I request you to see if the first and the fourth index, if you contract, it will still be 0. Now, from the 4-index object, we have come to a 2-index object. Now we'll define a scalar which is defined in the following way. So we call it R. So all of these are called R for Richie. So this is G alpha beta, R alpha, R beta. Sorry, R alpha beta. So it's contracting the Richie scalar itself. So that is my definition of R. And you can imagine that this I can write as G alpha beta and R eta alpha, say mu beta, and G eta mu. You can see if I write it this way, then so how can I write it this way? Well, this quantity, what it will do is that it will change eta to mu in the Riemann, and that will essentially become R mu alpha mu beta, which is R alpha beta. All right. So this is another scalar. So we are defining new things out of the 4-index object, the rank 4 tensor called the Riemann curvature tensor. We define Riccei's scalar and Riccei's tensor. Now what we will do is we will try to get to another tensor, which is one of the important tensor in general relativity, and we will see why its name will tell you that it is important. To go there, what we will do is we'll start with the Bianchi identity. So we'll start with Bianchi identity. The way to remember it is that you keep the first 2 index as it is, and then interchange the last 3 index. Remember that we wrote this as okay. Similarly, we wrote this as the first index and then interchange the next 3 index cyclically. So this was that. Okay, all right, let's see. This also is sometimes called the Bianchi identity. But let's see what we get here. So let's first start with, so our alpha beta mu nu semicolon lambda, just writing down that line here again, lambda mu semicolon nu plus r alpha beta nu lambda semicolon mu is 0. Okay, before I proceed further, let me remind you of something, that if I have the metric written this way, its covariant derivative is 0. But what about this? Well, this is also 0 because the matrix with the upstairs indices, G with the upstairs indices rather, depends all on G with the downstairs indices. So if I want to take the covariant derivative of G with the upstairs indices, it will eventually boil down to taking G derivatives with the G with the downstairs indices, and then it will be 0. And this makes life a lot simpler, because say if I this implies that if I have some tensor, say A, whatever be the index, say mu nu, and covariant derivative with eta, and say I multiply with some G alpha beta, then I can take G alpha beta inside the covariant derivative, because its covariant derivative is 0. This is a very useful tool which you may need to use sometime, and we will be using it right now. Like for example, here I will multiply from outside with G alpha mu. You see what it does to the first term. So as the G comes inside, alpha goes upstairs, so that becomes a Richie tensor. So it becomes R beta nu. What about the next term? Well, you see, if this was mu lambda instead of lambda mu, then again I will get a Richie tensor. But if I have to change it to mu lambda, I will get a minus sign for that as a penalty. So this will be R beta lambda semicolon nu. And in the last term, I can just bring it upstairs and make it mu, but I cannot do much because it is a derivative with respect to mu. And obviously, this is also 0. You do the same exercise once more, that now I multiply this with beta, say nu. Why do I do that? You can see that the first term just becomes R now. So this will become R once you do the multiplication. But just let me write down all the terms, and we'll do it in the next line. So the first term just becomes R semicolon lambda. R is the Richie scalar. The next term, see the beta becomes nu, so this becomes R nu lambda semicolon nu. What about the next term? Well, the next term is a little bit complicated because you have to bring the second index upstairs now. So I will just keep it as it is, because we have to go back one term to understand what is happening to that. So let us calculate this out. So I will do this in a different color such that we understand it is an inline calculation. This quantity, this R, we got by doing G alpha mu. So I'm reversing the step, and then R alpha beta nu lambda semicolon mu. Okay, so let's see what we can do. We can exchange the first two index in penalty of a minus sign, and we'll see once I do this, now this and this will give me a Richie. G alpha mu, and the first and the third index got contracted, so this is alpha lambda comma mu, and you get, once I use the contraction with G, I get mu lambda semicolon mu, which is, this term looks exactly or actually the same as that term. So let us now write this down with white again, that this is R. I get 2 of this term. We define, if we define the following tensor, now we'll see this tensor is related to the previous line. Let's just show it to you. Let me just show it to you. This is our alpha beta semicolon alpha plus half R semicolon alpha G alpha beta, which I will get if I just multiply a G with this expression. So first we get this tensor, and this is the famous celebrated Einstein's tensor. And we also realized this is equals to 0. This is also sometimes called the Bianchi identity. Now, if you look at the construction of the Einstein tensor, you see that I have R alpha beta, and remember that R is symmetric. I have G alpha beta, which is also symmetric. So this is a symmetric second rank tensor. In general, it has 10 independent components. And this itself is one of the famous equation in GR. We will see later that this will account for the equations for getting the general relativity or the gravity when there is no source. But we will come back to that maybe in the next lecture. So what have we learned? So this completes kind of our discussion on geometry. What have we learned? So let me go back to the beginning of today's lecture. Last time we defined the Riemann curvature tensor, which is a rank 4 tensor, and wrote it down in terms of the Christoffel symbols or the affine connections. We showed how it reduces to the local inertial frame. We looked at its identities, and today we define the Richie tensor and the Richie scalar, and then eventually the Einstein tensor, which is what we will be using shortly. All right. In the rest of the lecture, what we will try to do now, from now on, we'll try to connect physics with this working in the curved space-time and this complicated remaining geometry. So for that, let us go back to the equivalence principle and let us remind of what was the equivalence principle. So freely falling observers constitute local inertial frame and in this local inertial frame the laws of special relativity holds. So all I have to do is for the locality I have to just go to the freely falling observers instead of observers stationary. Next, the effect of gravity, or let me say the real effect of gravity, which cannot be just taken away by the freely falling observers, is in how the trajectories of the freely falling observer differ. So what do I mean by that? Well, if there is a uniform gravitational field, so this is essentially non-uniform gravity. If there is an uniform gravitational field, it can be completely get rid of by going to a local inertial frame defined by the freely falling observers. But if there is gravity which is changing at space to space, I cannot do this. Okay, so what we will do first is to look at what do you mean, what is the effect of a non-constant or non-uniform gravity in Newtonian framework. Okay, so effect of non-uniform gravity. So what we consider are two observers. They are moving in a gravitational field in two trajectories, and they're filling with the trajectory, so they're filling gravity. So there is a origin somewhere here, and an instantaneous position of the observer A is this. So this is my radius vector if you wish. At the same time, the observer B is here. Remember that the parameter in case of Newtonian mechanics is nothing but time. So when I talk about the instantaneous position of these observers, so which is a 3 vector, it's say x1 as a function of time, and this is x2 as a function of time. And the index L tells you that it's a 3 vector, so there are 3 positions. So I have two trajectories. So how do I write the trajectories? Well, x1L, which is the position, is given by this function x1L as a function of t, and x2L function of t. And we also define the deviation between the trajectory, which is nothing but x2L minus x1L, which I call xi as a function of t. Alright, so we are doing all Newtonian gravity here, there is no general relativity. So you have a force called gravity, we have no curvature, nothing, it's a flat space time. So you are dealing with flat space time, there is no space time also, so flat space. And only Newtonian gravity, I have a gravitational force. So I can write down the accelerations. The acceleration, so it's x1 double dot L. This will be given by x1 double dot L is the acceleration at A, say. So this is the derivative of the gravitational potential taken at A. So the potential, and it's also constant by the way, so it's phi. It's a function of all x. So you take the derivative at A and take a negative gradient, that is the definition of it by Newtonian gravity, that is the acceleration. x2, this I can write the same way, but now at B. And what we will do is we will just do it, we say that A and B are very nearby, so I can do a Taylor expansion. So this phi at that point is this, plus the relative separation, which is xi, times the derivative along the direction of xi. So if I call this m, so this becomes a second derivative of phi. So this is nothing but Taylor expansion. If you think about it a little bit, it is easy to understand. Taylor expansion, so this separation is xi. So along the xi, we have taken the Taylor expansion. The potential at A plus the little change in the first order to go to B. What does it tell us? Acceleration of the deviation. So what I mean by acceleration of the deviation is just xi2 double dot, and we realize that this is nothing but x2 double dot L minus x1 double dot L. So the phi A cancels out, this is just xi m, and then the second derivative of phi. And all this has to be taken at A, remember, that is a Taylor series expansion. This is what I get as the deviation between the trajectory. And you see a very interesting thing. There is no deviation if the potential is uniform. This is interesting because what it is telling you that if the observer, so now imagine that there are two observers passing by these two trajectories, and they're at the point, they're at different time, they're at different points in the trajectory. But as one observer looks at the other, if the gravitational field is completely uniform, then they will see nothing changing. For them, the other observer will be always stationary. This essentially is the equivalence principle. It's telling you that in a uniform gravitational field, for these observers who are moving in the gravitational force, so they are kind of freely falling observer, right? So for those freely falling observers' point of view, there is no deviation between their distances. They are kind of stationary observers. But if there is a change in the potential, or change in the potential rather, then they will feel that one is accelerating with respect to the other. Okay, so this is that completely from a Newtonian perspective. We have not used any general relativity, anything from geometry or anything from the equivalence principle here. Let's look at the same thing in terms of general relativity. So first thing we say here is that there is no force. They move in their geodesic curves. Okay, they're just moving in their geodesics. There is no other thing, there is no force acting on them. So what we are considering now? So we are considering the picture is the following, that there are these nearby trajectories. They're all geodesics. In some space-time of some observers, each geodesic and as I have drawn it, it is clear that I am allowing for any curvature if there is. So if geodesic is defined by a parameter, so lambda obviously changes along the geodesic. Different geodesic maps lambda to different curves. Obviously, there are different geodesics we are considering, nearby geodesics. So something has to change along this curve. We call that, so that there is a parameter, say eta, which changes as you go from one geodesic to other. and says that so this is a very little change, so the trajectories will differ by a little bit only. The trajectories will depend both on lambda and eta. So let's define the trajectories. Well, it's just writing that x alpha, now alpha can be 0, 1, 2, 3. This is just equals, I'm sorry, uh, this x alpha is the value in the trajectory you get by putting in the value of lambda in the functions x alpha lambda. And the tangent vectors, we can also define the tangent vectors along the curve. The tangent vectors along the geodesics are nothing but the velocity, the four velocities, which are given by dx alpha d lambda. Now, it may not be quite the four velocities if lambda is the not the time, but let's call that four velocity for the time being. If lambda is tau, the proper time, then it is the four velocity. Now, since they're geodesics, it's not any other curve, it's a special curve which is the shortest, which is along which you always get the shortest distance between the points which lies in the curve. So you must have this satisfied. That is essentially the geodesic equation written in short form. I can also write this in a little different notation. I can write this as this also, or I can even write this this way also. It's just notations. Now, just like earlier we talked about a deviation between the trajectories, here also we'll talk about a deviation between the trajectories. And the separation between the trajectories, or the deviation between the trajectories, will happen because of this parameter eta. So I can call the separation between the trajectories, just like I have the tangent vectors that goes along the trajectory, the separation vector, or you can call it a deviation vector also. I call it xi here also. Now this will be the change in x as a function of eta, because that is what changes trajectory to trajectory. Now let us calculate an identity, or two identities. This has some geometrical significance, but probably we'll skip that for this particular course. So u alpha, I take a covariant derivative of xi beta like this, and I calculate this minus this quantity. Okay. Now remember that x changes because of lambda only, but that function x also is different for different eta. So to remember that, so the function x, the functions, this is the function itself is different. It's not the value that is different. Is different for different lambda. Sorry, different eta. With lambda it does change, so that is what is meaning by geodesic. So because of that, I doesn't write it as just total derivative. I write it as a partial derivative. Just to remember that this x alpha as a function can also change with eta. All right. I'm not sure how mathematically correct it is, but maybe always we don't need to be exactly mathematically correct. Anyway, so this is xi alpha. Xi alpha is, remember that del x, again, it doesn't only change with eta, it also changes with lambda. So I write it this way. And here I have del of u beta del x alpha. So if I do the so this is del x alpha del x alpha. So if I use the partial derivative sum rule, so then this is derivative of xi beta with respect to del lambda. But then you remember that xi beta is also nothing but x beta del x eta. Similarly, here also this becomes a derivative with respect to eta only, but u beta is del x beta and del x lambda. And you realize that they're same, so this equals to is 0. A more interesting identity will be that if I now, instead of writing it this way, if I say that xi beta, what I wrote is here comma alpha, but if I instead write the covariant alpha, and it is easy to show that is also 0. This I leave it to you as homework. It's very straightforward once you have written down, once you have proved this identity. All right. Let us ask the question now. We are interested in how does the separation vector changes at the geodesic progresses. So let us define the change in the separation vector. So this we called the velocity. So it's v alpha. This is the velocity that one observer will see the other observer having. That's the idea, that both of them are freely falling in their own geodesics. One observer looks at the other, and does he see that is going away or coming towards him? So this I define as is just a covariant derivative of xi. And then the acceleration, which is the covariant derivative of v. This like velocity, like acceleration. Okay, what we are interested in is to figure out what is A alpha. Okay, so let us calculate that. This should be A beta, not alpha. So A beta is u eta this I can replace as Let's use some shorthand notation because otherwise it will become quite complicated. What I have here, if you remember the notation I used here, this basically means that you have u beta in this case, and you are taking a covariant derivative along the direction of the vector u. So let's write that in this spirit. So I have taken a covariant derivative here in the direction of vector u of a covariant derivative which is in the direction of vector xi. I'm sorry, which is in the direction of vector u again of xi beta. What we have just shown here, if I write this down in this language, this is covariant derivative in the direction of u of xi beta. That is same as, if I switch the minus to the other side, covariant derivative in the direction of xi of u beta. These are same expressions. So this I can write as let's work this out. Now we can write in components. Right? Now the covariant derivatives follow Leibniz rule, which means that I can do the derivative of the first, which is in this case, and keep the second intact. And then do the reverse. Now here again I can use the same identity and change the first term in the bracket as xi alpha and then del alpha u alpha. No, sorry. Eta here. This term, something interesting happens, so this should be a plus sign here. Something interesting has happened already here. You see that I have this type of term, which is the double derivative with respect to double derivative of double covariant derivative. And remember that this we have shown earlier. I'm just putting both the sides in the same side. So this I can use now. So I will have two terms here. In this stage, let me write down this only. So here I will have two terms. And I get the Riemann. Nice. At least I have got something which looks like familiar. You see that alpha is a dummy index here and eta is also a dummy index. I can interchange them. So this becomes xi eta u alpha plus u alpha xi eta I had u alpha xi eta here also, which I forgot to write down. Now let's look at the first two terms. What do I have here? I can write the first two terms. You see, I have here u alpha outside and the second derivative of and the derivative of grad alpha u beta. Here I have derivative of u alpha and keeping grad alpha u beta outside. So it's like Lembridge rule. So if I take xi eta common, this is nothing but grad eta of this entire thing, which is u alpha grad alpha u beta. So once you take the derivative of u alpha only, keeping grad alpha u beta outside, you get the first term and then you get the second term and you do the other one. What is this? Well, this is just the geodesic equation. This equals to 0 is the geodesic equation. U alpha grad alpha u beta equals to 0 is the geodesic equation. So because we are dealing with geodesics, so this is essentially 0, which tells us that a beta is minus r beta delta alpha eta u delta u alpha xi eta. Or if I just define something like k beta eta, which is just considering all three of these, this is what I get. The acceleration. So what is this acceleration? Remember, there are two observers freely falling into nearby geodesics. One will see the other having this acceleration. So this is the acceleration that one freely falling observer will see for the other. And And this is non-zero when you have the Riemann curvature tensor non-zero. If I compare this with the acceleration that we got earlier, which was this was the acceleration that we got earlier. So this is Newtonian, and now in spite of having absolutely zero concept of force, we still get exactly same looking acceleration. If you identify that second derivative of potential with that k over there, it is exactly the same equation. What has happened? We have realized that a changing potential, or a potential which is non-uniform, or the in second order if you wish, is essentially equivalent to a curvature in space-time. So this is the relation between the space-time curvature and the potential in the Newtonian gravity. So the potential in the Newtonian gravity can be completely replaced by a curvature in space-time, and you see the curvature is zero if the potential is such that its second derivative vanishes. Okay, so this is the connection between the geometry of the space-time and gravity. You realize that I don't need any force anymore, and the potential that we talk about of the gravity is all there in the curvature of the space-time. That replaces all that you think of as potential. I'll stop here today, and we'll start looking at more interesting thing, and finally develop or write down the final theory of general relativity in the next lecture. Thank you.